I got asked by Doug Newcomb to come and talk about the ESA, European Space Agency's Sentinels series of satellites today. And I know that most of your work is more on a geodatabase and sort of vector operations. I know imagery makes its way into a lot of your work, and it's usually aerial imagery and stuff like this, but I just want to make you aware of sort of the orbital platforms that we have now. And we're getting to where I think you could use a lot of these in your own workflows if you haven't already, particularly around classification. And we have some really high resolution stuff and some very interesting satellite platforms allowing us to do things like radar and stuff. So I'm going to talk about the Sentinel project here. So let's go. So the Sentinels are missions that fall under this heading at ESA called Copernicus, the European Earth Observation Program. And their goals are stated here, stolen directly from their website without quotation marks. Accurate, timely, easily accessible information for land management, marine environment, atmosphere, emergency response, security, and climate change. This program was formerly known as GEMS, the Global Monitoring for Environment and Security Program. Copernicus has a little bit better ring to it. So the Sentinel concept, 6 satellites, you'll see why there's an asterisk there in a moment, each comprising 2, also with an asterisk, satellite constellations that carry a variety of different instruments. That should also have an asterisk because some only have 1 and some have up to 5, so we'll talk about that mostly. So the first satellite constellation, or the first, really, these Sentinels should be thought of as missions, not individual birds, because some of them have 2 and some only have 1. So the first mission, Sentinel-1, is a C-band polar orbiting synthetic aperture radar. Its heritage instruments include the Earth Resource Satellites 1 and 2, InvaSat and RadarSat. Both Sentinel-1A and 1B, so the full Sentinel-1 constellation is active right now. So they launched the first Sentinel back in April of 2014, and this past April, Sentinel-1B got on orbit. They're both functioning very well, and they're turning out some really amazing data. I'm going to have to start completely over. The whole Earth is imaged every 6 days with these instruments. There's a variety of different modes that this instrument can operate in, from a interferometric wide swath mode, that's the default mode. There's an extra wide swath mode, a wave mode, which is quite interesting, and a strip map mode. And the strip map is for heritage data continuity with InvaSat and RadarSat. There's dual or single polarization modes for most all of these collection modes. The applications are mainly going to be used for CI, surface deformation, soil and soil water, and things like that. So the spatial resolution depends a lot on what mode it is, but they range from 20 to 40 meter pixels in the default mode down to 5 by 5 meter pixels in that wave mode. So you can have some really highly detailed information. Pretty amazing for a radar that's 900 kilometers in the air. So the land default, as I mentioned, so when it's collecting over land, the default is this interferometric wide swath mode. So it's a 250 kilometer wide swath, 5 by 20 meter pixel resolution. So that's odd pixel sizes. We're not necessarily used to that when we're in the optical remote sensing world, but that's a synthetic aperture radar sort of thing. So you have a better resolution across track than you do a long track, or vice versa. I forget. Here's an example, a little beauty shot of what it might look like orbiting the Earth and demonstrating 2 of the different modes. So you can see the top is the normal IWS collection mode, comprised of 3 individual scans put together. And then what you see below is a simulation of what this wave mode would look like. The wave mode is called wave mode because it's meant to detect wave motion on the ocean. So it actually is just sampling every 100 kilometers into a little grid like that. And within that grid, within that smaller footprint, 5 by 5 meter resolution at a variety of different polarizations. So you can do things like how big are the waves and which direction are the currents and things like that. Here's an example of an application of it, some results from Sentinel-1 data. So back in 2016, October 30th, there was an earthquake here in Italy. And so what you're seeing is actually the east to west shift in the land surface. This is taken from, I think the first image was collected the 25th of October, and then, of course, 6-day repeat. So we had the day after this event on Halloween. We got to see this area again. And so this is the change in the east-west direction following that event. So you can see the town, I won't pronounce the name properly, but Montegallo has a positive shift of around 30 to 40 centimeters, and whereas this Nortia shift in the other direction, 30 to 45 centimeters. So time to update your ground control points and your geodetic datums if you're in those areas, right? Here's another really beautiful example. This is the Virunga Mountains. This is on the border of Rwanda and Congo. What's really interesting to see here is that this is a protected area, and so you can really see the boundary of the protected area. Where you see green and orange and yellow, it means that there's been changes in the surface height mainly, or maybe even surface roughness, some condition of the surface, usually related to vegetation changes here. So you can see these hard boundaries that define the protected areas versus the non-protected areas which are cultivated. In particular, this gridding pattern right here, it's not an artifact, that's of course agriculture, right? So we can actually see this really high resolution, fine detailed changes. Irish potatoes, that's what they're growing here? Well, there you go, see, I learned something new. Irish potatoes in Congo. I'm skipping ahead here, okay. So Sentinel-2, this is the one that you're probably most interested in. You may have already heard about. It's the most familiar to us that are coming from a Landsat world. So this is a very Landsat 9.0 sort of satellite, right? It's a polar orbiting, wide swath, high resolution, multispectral, broadband multispectral imager, okay? So the first launch, 1A, is on orbit, delivering just beautiful imagery right now. It was launched last summer. And 2B is coming up here in just 2 weeks is the planned launch. So hopefully that gets on orbit nominally as well. So it has a 5-day revisit when you have the 2 satellite constellations. Right now we have a 10-day revisit. For comparison, Landsat's around 16 days before Landsat comes back. But we have 2 Landsats currently operating. Well, 1.5. Landsat 7 is broken, but still coming. And they're offset by 8 days. So we have a basically 8-day repeat for Landsat. With these guys, we get a little bit wider swath. And so we get 5-day revisit when we have this double constellation. We'll return to this sort of at the end because when you use this with Landsat, you get 2 to 3 day repeat over almost the entire Earth's surface, which is really fantastic at the resolutions that they're offering. So it's a multispectral imager, 13 spectral bands ranging from roughly blue, green, all the way out into the sort of short to long wave infrared stuff. But it doesn't have a thermal imaging instrument, unlike Landsat, which has the Landsat OLI, or Landsat 8 carries OLI, the operational land imager, and TIRS, a thermal imaging radio spectrometer. This one doesn't have a thermal instrument. Thermal instruments tend to be really expensive and hard to make. And in fact, Landsat 8 wasn't planned to have one and sort of bolted on at the last minute, quite literally. And so we don't have that, but within these bands that we do have, these 13 spectral bands, we have really fantastic resolution. So for 4 of the bands, we have 10-meter resolution. We have 20-meter resolution in a little bit of the longer wave bands, narrower spectral ranges. And then at the longer wavelengths where we have less and less photons to sense, we have to look at a bigger area to get enough to overcome the signal-to-noise ratio. We're at 60 meters, but only for the sort of shortwave infrared stuff. Applications, very familiar applications to us, right? Vegetation status, health, agriculture, land cover, land use change, all the sort of optical, vis, near-infrared, remote sensing applications that we're all familiar with. There's another little beauty shot, sort of showing how it has these 13 different spectral bands across a wide range of colors, and showing its sort of nominal swath width there. I don't know where in the world that is. Anybody? Well, it's definitely Photoshop. It's not. Yeah. I know. There we go. Oh, this is Italy, right? Yeah, there's Italy, Cyprus. Okay, perfect. There we are. And because oftentimes you see these beauty shots or renderings, you don't really have an appreciation of what the scale is of these things, right? Are they the size of a toaster or the size of a school bus? Closer to a school bus. So here is the Sentinel 1A instrument going into its payload fairing to be carried on top of Ariane rocket. And so it's a pretty big instrument. A couple of tons. Apparently takes that to get the type of quality data that we'd like to get. I say this is in comparison to Planet. I don't know if you guys saw, but the company Planet, formerly known as Planet Labs, put 88 satellites into constellation last week, set a record for the most put on orbit at once. And those things are the size of a toaster. So they're like a cell phone with a cell phone camera and a solar panel orbiting the Earth. But they're turning out some very interesting data as well. Here's an example of some Sentinel 2A data. This is Madeira. There was a big fire that happened here in Madeira off the Portuguese coast. So this shows the entire island. And then we zoom in, and the fire scar itself is actually very obvious here in this false color representation. I've never been to Madeira, but it's not red like that, I don't think. Here's just something that's quite beautiful. It looks like a watercolor painting, but this is actually the Barents Sea between Norway and Russia and above Finland. So this is a phytoplankton bloom in the Barents Sea that was captured by Sentinels 2A. This is close to true colors you can get with these sort of narrower bands. And then because I primarily study agriculture and I never get over looking at crop circles, this is crop circles in Saudi Arabia of all places. So they grow a lot of wheat, chickpeas, and things like that. Of course, it's the middle of the desert, so it has to be irrigated. These are pivot irrigation machines. For those of you unfamiliar, the size of these things, the standard machine is called a quarter-mile machine, which is the radius of these circles. So each of these circles might be a half-mile across, and they have even longer ones that could be, 3/4 or a whole mile across. So it's pretty amazing sort of transformation of the landscape there. But another thing that you can note here is the resolution. 10-meter multispectral imagery here is very fantastic. Since we talk about it as a sort of Landsat-like sensor, it makes sense to sort of look at the different spectral bands here. Landsat 7 along the bottom, its bandwidth's numbered. Also Landsat 8 directly above that. Very similar instruments between OLI and ETM Plus in the Landsat world. Again, we have thermal imagers, band 6 for Landsat 7, and then we have 2 different ranges for tiers. Mostly the same bands otherwise, except OLI grabs a coastal band, and then it grabs this band 9 for cloud cover. So you can see Sentinel carries a lot of the same sort of spectral ranges. It has some much finer spectral ranges, 5, 6, 7, and 8A, and then it has additional sort of atmospheric correction bands, 1, 9, and 10. 10 and 9 are very similar between Landsat 8 and OLI. As are 1, it has an additional one in this atmospheric absorption channel right here. So the background is sort of solar irradiance with atmospheric absorption on top of it. So where you see these dips are places where we don't get a lot of radiance reaching the Earth's surface, right? So we want to put those collection bands in there to understand what the atmosphere is doing. And then the 3 different, the vertical staggering here, 60 meters at the top for 1, 9, and 10. Again, they're very, very tiny range. And then 20 meters for 5, 6, 7, 8A, 11, and 12. And then 2, 3, 4, and 8 channels down in the vis and near infrared are all 10 meters. Sentinel 3. Sentinel 3, the third mission, is primarily meant for ocean observing, but it carries an instrument that is very MODIS-like. So if you're familiar with NASA's 2-satellite constellation, Terra and Aqua, they both carry an instrument called MODIS, which collects 36 very narrow spectral bands that's used for global sort of coverage. They see the whole Earth twice a day, a morning and an afternoon overpass. This is carries a very similar instrument called the OLCI, the Ocean and Land Color Instrument. Itself has 21 spectral bands, cuts a 1,270 kilometer swath. It carries another instrument called the Sea and Land Surface Temperature Radiometer, which has 0.3 Kelvin accuracy land and ocean surface temperature imaging capability, which is really fantastic. 0.3 degrees. So that's pretty wild. It also carries 2 microwave imagers. It carries the SRAL, which is a synthetic aperture, the SAR radar altimeter, and the MR, the microwave radiometer. So they have different revisit times because each of the instruments has a different swath and a different sampling pattern. But OLCI, the MODIS-like instrument, every 2 days, repeat, and it'll offer imagery. Sorry I didn't put that up here, but imagery from OLCI has a 300-meter nominal ground resolution. And then the SLSTR, I think that's around a kilometer ground resolution, and it can image the whole Earth every day. And then for the radar altimeter, we have a much narrower band, much narrower swath, And so it's greater than 27, 28-day repeat there. But that stuff's mainly used for sort of ice surface, ice sheet deformation and stuff like that. So things are moving a little more slowly there at the moment. So one of the birds is already up. 3A is on orbit as of February 16th, 2016. We have another one planned to launch sometime this year. They haven't put a finer point on it than 2017 right now. They're also, here's where the asterisk comes on the 2, is that they like this guy so much, they ordered 2 more. So there's also going to be a 3C and a 3D launching sometime in the 2021 and beyond framework. So most of these Sentinel missions have lifetimes between 7 and 9 years, and so you'll see a lot of the sort of planning for the launches takes that into account. So I think they want these data to be have continuity, so they're going to launch 3C and 3D, and we'll have pretty good coverage out into the 2030s if that actually happens. So 3C is already built, 3D is already ordered, so hopefully those get into orbit. Again, the applications include sea level, sea surface temperature and land surface temperature, water quality, sea ice thickness, land cover monitoring, that sort of thing. All this sort of stuff that we can do with MODIS, plus we have this radar altimeter. So here's sort of what it might look like if you were up there orbiting right beside it. And here's an example of imagery from Sentinel-3A. This is the Fort McMurray wildfires in Alberta. So this actually shows you 2 dimensions of the information. This, the OLCI, the Ocean and Land Color Imager, in as close to true color representation that we can get. And then this is the temperature sensor is the red. And then is drawing your attention to the wildfires here. You can see they're going to turn out to be very bright because they're very hot indeed. And in this image, they're highlighted here as pinpoints. But it's actually saturated the red band, whatever's assigned to the red channel here because it's so hot. Here's another one of first level data from the radiometer. It shows the brightness temperature, which corresponds to radiation emitted from the surface. This is converted to Kelvin temperature, so surface temperature of Italy and the surrounding ocean. And again, I say this is 0.3 Kelvin accuracy, so that's very nice. Sentinel-4, now we're getting into things that have not yet launched. We don't have any of the things Sentinel-4, 5, 5P, and 6 have yet to launch, but they're planned in the next few years. So this one, unlike the polar orbiting sun, everything that I mentioned previously is polar orbiting sun synchronous. So it's between 700 and 900 kilometers above the Earth. This guy, way far out there, 36,000 kilometers away at the equator. It's going to be on board a geostationary satellite, Meteosat. It's going to image the full disk of the Earth centered over Europe and North Africa. Okay? So we're out of luck for instrument if we need to see the United States on this, but there are other geostationary satellites that we have that provide similar information. It carries 2 hyperspectral instruments. Hyperspectral meaning that the wavelengths that it samples are very fine bands, very narrow bands. The ultraviolet visible near infrared spectrometer and the infrared sounder. Both of those. So in the UV, ultraviolet and visible range, we have 0.5 nanometer spacing on the spectral channels, very fine indeed, and we do even better at the longer resolution in the near infrared, 0.12 nanometers. So we can really start to get at sort of functional traits and things like that with these very, very precise spectral measurements. 8 kilometer sampling, again, it's a sounding instrument. It's not an imaging instrument. So if you're familiar with the Orbiting Carbon Observatory, OCO2, you know it doesn't create images, it creates samples. This is exactly like that. It creates samples across a grid. It's a sounder, not an imager. So the launches are planned in 2019, 2027. This is primarily an air quality monitoring instrument. It can atmospheric gases, carbon monoxide, sulfur dioxide, nitrogen oxide, these sorts of things. You can measure that with these spectral observations. This is what it will look like with Earth very, very far away. Earth is likely to look a little bit smaller if you're all the way out there. Sentinel-5P, here's another one where the asterisk on the 2 comes in because there's only going to be one of these guys, and it's a sort of added-on, tacked-on mission. It doesn't even get its own name. It's called Sentinel-5 Precursor, and its main purpose in life is to get onto orbit really quick with not the most cutting edge or the future sort of instrument technology, solely so that we can provide data continuity with the Invisat sensor. I'm not even going to try to pronounce that acronym, though I think it's pronounceable. I will pronounce OMI. It's a NASA sensor called AURA. It's in the NASA's A-Train along with Terra. OME satellite to bridge the gap before Sentinel-5, because Sentinel-5 will not make orbit by the time these satellites are at end of life, and this information is critical. So they're going to launch 5P, which they can produce pretty quick with basically off-the-shelf components and technology, and get it in orbit pretty quick. It is a polar orbiting sun-synchronous, global daily coverage. So it carries a single instrument, tropomy. It's a hyperspectral imager, UV, vis, near-infrared, and SWIR. 2,600 kilometer swath, 7 kilometer resolutions. Again, this is air quality monitoring. So we're looking at atmospheric gases, ozone, aerosols, methane, monoxide, those sorts of things. It's a cute sensor. Here's some example data. This is, of course, not real data because it's not on orbit, but this is from that unpronounceable sensor, Shiamaki. And this is a methane product that's produced from that sensor over 3 large-scale fracking sites in the United States. So we have Marcellus, Bakken, and Eagle Ford, and you can see these fracking sites delimited. I don't know what the polygon means, but you can see that we have high methane concentrations centered on these fracking operations. So methane's one of the things that they can sense. Here's another one from OME. This is the formaldehyde product. I think this is actually really cool stuff. This is September, so we don't have much going on vegetation-wise in the northern hemisphere, but we see high formaldehyde concentrations in the atmosphere over the Amazon, some over the Congo, and of course throughout the tropical forests in the Pacific Ocean. So what's happening there? These trees, as they photosynthesize, release isoprenes. Isoprenes can get up into the atmosphere, and through they get photochemically oxidized, and part of the byproduct of that oxidation process is formaldehyde. So we can use formaldehyde as a proxy for VOCs, volatile organic compounds, isoprenes, and things like this. So this is a very interesting product, and this is just one of the sort of things that you can get if you have a really nice hyperspectral imager. And so we expect that Sentinel-5P is going to offer data very similar to these two instruments, OME and Shiamaki. Sentinel-5, back onto the sort of two-bird constellation deal. Now we're back into the polar orbiting world. Actually, 5P was as well. Sun synchronous is on board the MEDOP satellite. Planned launches in 2021, and then shortly thereafter, 2022, will be 5A and 5B. It carries a single hyperspectral instrument over 7 different distinct ranges. 50 by 50 kilometer resolution at the UV1, 7.5 kilometer resolution for everything else. Big swath, enabling near daily coverage. Again, this is atmospheric gas measurements, aerosol, optical depth. So 5P, 4, 5, and 5P are all part of Copernicus atmospheric monitoring system, CAMS. And so they're all meant to take a different look at the atmosphere. Here's what it might look like once it gets built. And finally, the last one, the caboose. There's very, very little information about this guy yet. Sentinel-6, also known as JASON-CS. It's a heritage satellite from JASON and Cryosat. It's a polar orbiting radar altimeter, mainly to look at ocean topography, currents, wind speed, wave height, ice sheets, and things like this. So it's a radar altimeter that will look maybe something like that. And here's an example of data from JASON-3, which got on orbit sometime last year. And so we expect the data that we'll get to be very similar to this. So this is a sea surface height. Of course, we're used to saying above sea level, but sea level turns out to be quite different. And in fact, that's what drives El Nino. So right here in February of last year, you can see the El Nino indicated by above average, a buildup of water here in the Eastern Pacific, and a big deficit of water in the Western Pacific that really changes that circulation pattern. So that's indicative of an El Nino, and one of the reasons why we want to be able to monitor this sorts of stuff from orbit. You can get all of these data. They're meant to be accessible, which means that they are free and open source. Free as in beer, right? Free as in pizza. Is that what the saying is, Vashuk? You get the data here. The address is there at the top, scihub.copernicus.eu, Copernicus Open Access Data Hub. Once you go there and register, which is instant, you'll get something like this, a very nice map, lots of different options for how you can search and pare down the data, and then you can directly just start downloading the data. I need to plug this product because I'm part of the science team that is meant to figure out how we can use Sentinel and Landsat data together. It's a NASA project called MUSELI, the multi-source land imaging team. And one of the projects under that heading is called Harmonized Landsat Sentinel-2, or HLS. And so HLS is trying to take Sentinel data and make it continuous with Landsat. So they're at different spectral resolutions, and if you recall the sort of spectral bands, they're close but not quite exactly the same. And so this aims to take care of those differences. So it actually resamples that really great high-resolution Sentinel stuff up to that coarse old 30-meter Landsat, but it also does the spectral bandpass conversion, so that what we call near-infrared in Landsat is as close to possible as what Sentinel calls near-infrared. So it does that conversion for us. So like I said, when we can do that sort of thing and we have all these guys operational, we'll have 30-meter data or better every 2 to 3 days across the entire world, which is going to open up all sorts of things that we haven't even been able to imagine before at these sorts of resolutions. So the MODIS sort of era for the past decade and a half has been all about creating products, which is like you don't want necessarily to become a remote sensing scientist, but you need global leaf area index or you need global land cover, but you don't want to go through the process of fitting an LAI model or doing the classification so to create these products. But you were all on your own when it came to Landsat and 30-meter resolution. We are moving into this era of Landsat products very rapidly. So we'll have global 30-meter products, things like land cover, leaf area index. We already have our first global 30-meter product. Matt Hansen's group has a global deforestation map that some of you may have seen that he produced on Google Earth Engine. So Google's been promoting that. So if you haven't seen it, go look at it. It's a fascinating map, but really unprecedented resolution for a product like that. So when we get this 2 to 3 day repeat, we can do these sorts of things, but on time series, and we can do things like phenology. And so here we can see an example in South Africa and southern France of crop phenology. And so you can see the red dots being Landsat, and then the blue dots being the harmonized Sentinel product at 30-meter resolution. So we're starting to fill in these gaps and get enough temporal resolution that we can fit reasonable time series models and do a pretty good job of saying when do the crops start growing and things like that. Big red box, warning, warning. Some registration issues were discovered in the process of the HLS and some of the other MUSELI sort of interoperability campaigns here. In certain areas, limited areas in Landsat where we have either few GCPs, ground control points, or poor GCPs, we find pretty bad image-to-image registration between Sentinel and Landsat, up to 35 meters. That's not very good. So that's not going to get fixed until 2018 because it requires reprocessing of the entire Landsat archive. But we identified the areas. They are working their best to put new, better GCPs on the ground. But it will take a little while for it to get completely reprocessed. So for right now, if you're living in a world where you download from the LP DAC and you take it for granted that things are exactly where they are, if you're going to use that along with Sentinel, you're going to need to think about registration. So kind of think back 10 years ago when we had to do this sort of image-to-image registration sort of thing. You can do that. You'll need to do that. Thankfully, there's tools like AROP from Fungal that will take care of that for you. If you're interested in the details of this, there's a great remote sensing environment article out last year from Story and colleagues that detail that whole thing. So just in conclusion, the Sentinel set of missions falls under Copernicus, and it's going to be a diverse array of orbital instruments that are going to monitor the land, the ocean, and atmosphere in support of scientific research, in support of land and ocean water management, disaster response, and even security. So there's a lot of stuff here. And the big point here, all free, all open. Go get it and use it. So this has been really, really important. So when I started grad school, we had 2 Landsat scenes because they were $6,000 a piece. And a year before I graduated, the Landsat archive completely opened and everything was free. And the proliferation of techniques and understanding and insights that we have about the Earth because of that opening of that archive is just amazing. So them adopting this policy from the very beginning is great. And it's even better because in the political context we're in right now, I don't know if any of you are aware, but there's a bill to completely defund NASA Earth Science making its way through the House right now. this may be our only source of such information, right? So get real familiar with our European counterparts and let your representatives know that you want NASA to do the same thing, but definitely be aware of this sort of alternative. So, I think that's it. So there may be time for questions.
Yeah. When did the ESA decide to shame NASA's?
Well, it's an interesting point. I mean, they are relying on NASA to a great degree, and NASA has been fantastic in sharing its vast knowledge that it's accumulated in deploying its own Earth observing system over the past several decades, and they wouldn't be close to where they're at right now without that sort of help. So it's certainly been a partnership, and they've worked very closely together, and it's very heartening to see that. But yeah, they've got a lot of money, and they're building the hottest sensors that they can. You know, Landsat 9 is likely to be amazing. If we get money, it's going to look a lot like Sentinel-2 or even better, right? But Landsat 8 was designed 10 years ago and just made it onto orbit 2 years ago, right? So these things take a long time, which is why defunding Earth science is not just going to set things back 2 years, because you don't just pull the thing off the shelf and start building the satellite. You redesign from the ground up, because there's new technology, there's new rockets, there's new everything, right? So this is 2-year delay, 4-year delay, whatever it might end up being, could be catastrophic. It's in the House right now. Yeah. All right. That's it.
Thanks, Sean.
Hey, thanks.